Welcome back to Solving Logarithmic Equations lesson, and now we'll continue with some practice questions. We'll start off with practice question A. Before you watch this video, try to practice these questions on your own and try to find resemblance between the equations in the practice with the examples taught before. So question A, or practice A, we have log with base 2 of 30x minus log with base 2 of 5 equals log with base 2 of 12. So first, inspect the bases. They must be the same. And then continue with the next step, which is combining the terms. So we have log with base 2 of 30x minus log with base 2 of 5. So because you have a minus, the terms are connected to each other by the quotient law of logarithms. So we'll bring them inside the same log as log with base 2 of 30x divided by 5. So divided by 5 again because it's a difference of logs. And on the other side, we have only one term, so we write it as is. So it doesn't combine with any other terms. So now we are at a step when we have a single log term in each side of the equation. The bases are the same, and that means the expressions inside the log must be equal. So our next step, we have 30x over 5 equals 12. Obviously, we'll simplify 30x over 5, so that divides to 6x, and then the right side is 12. Isolate x. This is a simple linear equation by dividing both sides by 6, and we get x equals 2. So this should be our solution, but before we make a final decision, we want to check and see if this solution works for our equation. The way we check is wherever you see x, you substitute it by your solution, which was 2, and see if the logarithmic term exists. So 30 times 2 would be positive 60, which means that x equals 2 works perfectly well for the first term, and there is no x's in the others, so we're going to accept x equals 2 as our solution. So next we're going to take a look at practice B. Again, we have to inspect the bases. In this case, you don't see the base of any of the terms, so we assume that this base must be equal to 10. So I'm going to write this base for now. Okay, but obviously, again, as I mentioned, we don't have to write it. Now, what's unique about this equation is that on the left side, you have log terms, and on the right side, you have just a constant number. If this happens in any log equations, what you want to do is bring all the log terms to one side of the equation and leave all the numbers or the constant terms or the regular terms to the other side. So in our case, we have all the log terms in one side and the constant number on the other side, so we can proceed with the next step, which is combining the terms. So on the left side, we have two terms we can combine. They're connected by the sign minus, which means that they must be connected by the quotient law. So we're going to rewrite this term as a single log term, and x will be in the numerator, and we are dividing. We said that's a quotient law, that's why. And then we're going to have this equal to 2. So as you can see here, we have a logarithmic statement. Log with base 10 of x over x squared equals 2. So in order to solve for x, which is inside the variable, we will have to convert this statement to exponential form. So in this case, we'll have x over x squared equals, the base would be 10, and the exponent will be 2, right? So this is the base, this is the power, or as we say, the log. So what we have in here is x over x squared equals 100. Now this is a rational equation, and the next step, as you may imagine, would be simplifying x. But when solving rational equations, I wouldn't do this because if we simplify an x, we can lose a solution. So we won't simplify x, but we will cross multiply both sides. And that will help us find all the solutions. In this case, we have x times 1 equals 100x squared. So I'm going to leave 100x squared on the left, x times 1 on the right side. And I will bring both terms to the left side of the equation. This is a polynomial equation of second degree. Factor out x. That's easy to solve by factoring. As you can see, we have a greatest common factor of x. And here we have 100x minus 1 equals 0. So as you can see here, we have two factors multiplying, which means that we will derive two solutions, one from making x equals 0 and one from making the other factor, 100x minus 1 equals 0, which makes x equal to 1 over 100. Now, these are the solutions that we obtained from solving this equation, and now we have to check and see if both solutions work, or which ones would be acceptable or not. So if you want to check for x equals 0, we always check in the original equation. So what you would have in here is log with base 10 of 0 minus log with base 10 of 0 squared equals 2. Now, as we have mentioned when we studied the graphs of logarithmic functions, the expression inside the log cannot equal 0 and cannot equal a negative number, which tells us that x equals 0 is an extraneous solution, or you don't admit this solution, so we don't accept this. When x equals 1 over 100, so if x equals 1 over 100, then the equation would be log with base 10 of 1 over 100. So that would be your first term, and this term exists. You can calculate it using a calculator. And log with base 10 of x squared will also be log with base 10 of x squared would be 100 squared, 1 over 100 squared, sorry. And again, this is a number that is positive in value, greater than 0. So both terms exist when x equals 1 over 100, so we're going to say that they're both acceptable solutions. The 1 over 100 will work for both terms, which gives the solution 1 over 100 a yes. So that would be the only answer in this case. Let's move on to another example. So this time we have log with base 2 of x plus 3 plus log with base 2x minus 3 equals 4. So let's get started. So again, inspect the bases. So we have base of 2, and then we have just a number on the other side. So all the log terms stay in one side, and then the number will stay on the other side of the equation. So combine the two terms. You see that they are added, which means that they are connected by the product law. So we'll bring them inside the same log term. So x plus 3, and then multiplied by x minus 3. So, and that would equal 4. So this is a logarithmic statement, and what we are going to do is, you can simplify this by the way, convert this logarithmic statement into an exponential statement. So what that means is that we're going to rewrite the same expression in exponential form. So we'll say that the expression inside the log, x squared minus 9, equals the base 2 to the power of 4. So let's see what we get. We have x squared minus 9 equals 2 to the power 4 is 16. So that makes x squared equal to 25. So bring negative 9 to the other side, becomes positive. And x must be plus or minus square root of 25, or even better, plus or minus 5. So as you can see here, in this case, we obtain two solutions. So one is x equals 5, and the other is x equals negative 5. So we will have to check and see which solution works. Why yes, why not? So remember that if x equals 5, then we will have log with base 2 of 5 plus 3 plus log with base 2 of 5 minus 3. So in this case, this log here would exist. It's log with base 2 of 8, and the other one would be log with base 2 of 2. So the expression inside the log is positive, which tells us that x equals 5 is an acceptable solution. So this is our first answer. Now let's check negative 5. So if x equals negative 5, then the first term, log with base 2 of x plus 3, will be log with base 2 of negative 5 plus 3, which is log with base 2 of negative 2. So the expression inside the log cannot be negative. Therefore, we're going to say that x equals -5 is not accepted. So next, we're going to take a look at a new group of equations. Now, these equations are given in exponential form, but we need to use the properties of logarithms in order to solve them. So let's start with example number 4. So what we have in here is 3 to the power of x equals 21. So our unknown, or the variable we need to solve for, is in the exponent. And this is an exponential statement. So to solve this equation, what we do is we rewrite this exponential statement into logarithmic form, and that would be log with base 3 of number 21. So this would be the exact answer to this equation. And if we want to find the approximate answer, and we often have to do this, especially if we are solving such equations for the purpose of graphing, we need to know the decimal or approximate value of the x so that we be able to plot the point on the Cartesian plane. So if this happens, then you know the rule. You just use a calculator to split this into log 21 over log 3. The calculators have a base 10, but if the calculator, your calculator allows you to input the base of the log, you just do it the normal way, just evaluate it in the calculator with this base. And if I use my calculator here, I would get x equals 2.77, and that would be the approximate or the rounded answer. So I'll round it here. So the approximate answer. All right, so let's move on to the next example, which is a kind of a more interesting example in a way. So when you look at the equation, you see that you have one exponential term on the left, one exponential term on the right side. When you look at the bases of each exponential term, they're different, and that's what makes the problem a little bit more interesting, okay? So remember that what we are trying to solve in here is x, and in both terms, x appears in the exponent. So to gain access to the exponent in each exponential term, what we do is we use the power law of logarithms, which I'm going to write down in here. Remember we said that log with base b of ax to the power of r equals r log with base b of x. That's a power law of logarithms. So what this does for our equation is that it will bring the power in front of the term, right? Make it into a coefficient, and this will make the power more accessible, and to us the power means making x more accessible. So usually what we like to do is take the log with base 10. It is important that we take the log with the same base, actually, but we are not limited to it. So one smart move that I would suggest that we can do in here is this. Now, we can choose the base of each side. So you can choose a base of 5, which will give you 2x plus 1, so that would be simpler. Or we can choose simply the base 10 for both sides, or you can choose the base 6 for each side. Now, most commonly, we use something that we call natural log, which for short is indicated by ln, which is a special base. It is log with base e, where e is a Euler number. Now, this is something that we will discuss in the coming lessons, but if you already know this, please know that it's a very, interesting and simple way of solving the equation. So for now, I'm going to leave the base at a base of 10, and I will simplify by using the power law of logarithms, which means that 2x plus 1 now will come to the front. And because 2x plus 1 is in binomial form, I will make sure that I keep it in brackets, because the entire power, which is 2x plus 1, is multiplied by log 5. In a similar way, we have x minus 2, and this will be multiplied by log of 6. So what we have done is getting x out of the log, but still we have x inside the bracket. So in order to access x inside the brackets, we'll expand. So what we have in here is 2x log 5. So that would be these terms together. And then we multiply log 5 by 1. That will give just log 5. And in the same way, we're going to multiply log 6 by x and by negative 2. So this would be x log 6 minus 2 log 6. So take a look at where your variable is located. So the variable is located here and here. And take a look at also the number of terms you have. So you have one term here. There is another term, another term, another term. So we have 4 terms in total, and only 2 of them contain x. So the terms that contain x must come to the left side. And I'm going to rewrite this as 2x log 5 minus x log 6 equals, I'm going to keep the negative 2 log 6 on the right side, and I'll bring over log of 5, which will change its sign from positive to a negative. So again, keep an eye on your variable. Remember, the variable must be isolated from the rest of the terms. And the best way to isolate this one here is by factoring x. So if you factor x out of 2x log 5, then we have 2 log 5 left. And then minus log 6 here. And that would equal, and what I'm going to do in this case, for the purpose of simplifying the answer, is I'm going to bring the negative 2 here in the power of 6, or you can leave it as is, because at the end we are just going to find the approximate answer. Okay. And lastly, we have to divide both sides by the coefficient of x. Now we have quite an interesting coefficient here for x. It's a numerical expression if you think about it, because it contains only numbers. And I know that log can make things a little bit uncomfortable, but remember, it's just a number. It's just another way of expressing a number. So we'll divide both sides by 2 log 5 minus log 6. So 2 log 5 minus log 6. And we'll say that x equals negative 2 log 6 minus log 5. I will try to combine the terms actually, because it will make the expression look and feel easier to simplify, to evaluate at the end. And we have log 6 to the power negative 2, and then minus log 5. And down here we have log 5 squared, and then minus log 6. Please avoid to make the mistake of simplifying these terms, because this log 5 in here and this log 5, they cannot simplify. That would be wrong, okay? Because you cannot simplify terms. You can only simplify them if there are factors in both numerator and denominator. It's a common mistake people make. And that would equal, if you simplify some more, so you have minus in between the terms, so that would be equal to log of 6 to the negative 2 will be basically 1 over 6 squared, and then divided by 5, because it's a difference between two log terms. And in the denominator, we have log of 5 squared, which is 25, and then we have that divided again by, we have that divided by 6, and that's because there is a difference between two log terms. So even simpler, this would turn into log of 1 over 6 squared, which is 36, times 1 over 5. We're just simplifying the expression inside the log, over log of 25 over 6. So that would equal log of 1 over 36 times 5, that would be 180. And that down here we have log of 25 over 6. So just use a calculator to find the value of this ratio. So basically I would leave the answer in this format for now, and I would say that the exact answer is log of 1 over 180. divided by log of 25 over 6. And if you want to find the approximate answer, what you want to do is just simply use the calculator for it. Now, keep in mind that when you use the calculator, you gotta actually put this in brackets, otherwise the 1 over 180 will divide the log instead of the entire expression, right? So you would actually make this expression different. Anyway, so here we go. We have log of 1 over 180 and then divide that by log of 25 over 6, and that gives negative 3.63. And that would be the approximate answer. Okay, so we're going to move on to our next example. So this time we have x to the power of log 2x equals 16. Now, as you can see in here, we have x appear in the exponent. So this is an exponential term to start with. The base of this exponential term is x. The exponent is log with base 2 of x. The value of that exponential term would be 16, okay? So x appears in two spots here. It appears in the base of the exponential number and inside the log, which is in the exponent. And there is no rule that we have learned to simplify this. So since this is an exponential statement, we can try to convert it into a logarithmic statement. That can be one way. And when this happens, then we will have log with base 2 of x equals, and then we have the base x to the power of 16. So having variables in both sides of the equation can be, I should say, interesting, but this cannot be the simplest way to solve the equation, because we will need to now express x in terms of this base and this power, which is going in circles. So the easier way to approach solving this equation would be by simply taking the log of both sides. So we're going to take the log of x to the power of log 2x, and we're going to take the log of 16. Okay. So obviously, for convenience, we usually take the log with base 10, and that solves our problems most of the time. But sometimes we have to use our intuition to simplify the coming steps by considering the base that we can give to the log that we're giving to each side. So in this case, because 16 is an exponential number with base 2, then it would be clever to use base of 2 for the right side term, so for log of 16. And in a way that can help with the other side as well. And that is because we have a base of 2 in the power as well. So in this case, we have log with base 2 of x, log with base 2 of x equals log with base 2 of 16. So I hope you can see here the power law of logarithms. So how? So this is the exponent, right? And the exponent can come to the front as a coefficient. So we're going to go ahead and write down here log with base 2 of x. So this log with base 2 of x will come here. And then we'll have log with base 2 of x as well, multiplying it. And that would equal log with base 2. Now think about 16 as an exponential number, can be 2 to the power of 4. So the right side is very easy to simplify. So you have one of the properties of logs here, log with base b of b to the x is x. So that would be equal to 4 in this case. I'm going to write the property on the side, so in case you don't remember right away. So log with base b of b to the power of x, we said, is equal to x. So whatever the power is. Now, on the left side, as you can see, we are multiplying two terms, and when you look at them, probably can easily see that these two are exact same terms multiplying each other. So there is no rule that connects two log terms multiplying. So do not confuse it when you add log terms. When you add, they are connected. If we had an addition, it would have been the product of the expressions inside. But this is not addition, this is multiplication. So the only way we can write this is log with base 2 of x to the power of 2. Why to the power of 2? Because we have a term multiplying itself. So we are trying to gain access to this x in here inside the log, right? So we have a power we need to take care of first, so power of 2. So in order to get rid of this, we're going to square root both sides. So if you square root both sides of the equation, we're going to get log with base 2 of x equals plus or minus the square root of 4, which is plus or minus 2. So we are deriving at this point two solutions here. So one that tells us that log with base 2 of x is 2, and one that tells us that log with base 2 of x can also equal negative 2. Now remember that the logs can equal negative 2 because logs are powers. Powers can be negative. It is only the expression inside the log that has to be positive, okay? So I'm just trying to add these reminders because from experience I remember and I know what are the misconceptions that we might have sometimes. So let's solve this very simple log equation. So convert the log statement into exponential. So we're going to say x that is inside the log must be base of 2, and we're talking about this base of 2 in here, to the power of 2. So it is this 2 in here to this power of 2 in here. So that will give x a value of 4. Now, if x log with base 2 of x is negative 2, that means that x must be 2 to the power negative 2, or 1 over 2 squared, or 1 over 4. So far we have derived two solutions, x equals 4 and x equals 1 over 4. So we have to check and see whether or not both solutions work. So if x equals 4, everything should work pretty well in here. And if x equals 1 over 4, there are no obstacles, so this is the base. 1 over 4 is expression inside log, is bigger than 0. So we're going to accept both answers. So they're both good solutions that we'd love to accept. Here we go. So we're gonna take a look at one more example, and this will be the last for this lesson. We have x to the power of root log x equals 10 to the power of 8. So in this case, what we're going to do again is take the log of both sides. So we're going to take the log of x to the power of square root log x equals log of 10 to the power of 8. Now, the base that I'd be most interested in keeping here is the base 10 because it simplifies this number very nicely, just like we did in the previous example when we took the base 2, right, so that we could get a nicer number on the other side. So in the next step, we are going to apply the power law of logarithms. So we're going to have the square root of log x multiplying log of x. So remember that, again, this exponent will become a coefficient, right? So it comes to the front, and this one here will stay as log x. They will stay together. The operation in between them is multiplication, right? And on the other side, we have log with base 10 of 8. Now, of 10 to the power of 8, so that means that the answer here will be 8, and this is one of the log properties we just mentioned. So when you look at this equation now, you notice that we have log of x, if you were to give it a power, would be power 1, and here we have again log of x, but in square root, which means square roots, remember, they're nothing but exponents, right, in rational form. So we'll have here log of x to the power of 1 over 2 times log of x to the power of 1. And in case you are wondering whether or not you could have simplified before, so write this with a rational exponent in the previous steps, you can definitely do that a lot faster than I am. I'm going slowly so that we don't get overwhelmed by the understanding, in the process of understanding the solution. So as you can see here, we have two exponential numbers with same base. So we are multiplying them, which means that we need to add the exponents. So that would be log with base x. Now remember that the entire log term is brought to the power of 1 over 2 plus 1 now. That would be 8, because that's the base of it. Okay, so the powers do not belong to just the expression inside the log. It's the log of x that is to the power of 1/2. So I know that I'm emphasizing the same thing over and over, but we just want to make sure here. So we have log of x to the power of, and this is how I do this. We have a half and a 1, so that's 1.5. In fraction form, 1.5 is 3 over 2. And if you don't want to do this way, you can just simply use a calculator. So the idea is that in order to solve for x, we will need an expression, or we need to solve first for log of x. So in other words, we need to start taking care of this exponent. So we want this exponent to be 1, right? So how can you make this exponent 1? Well, only if you multiply it by 2 over 3. So what can help us multiply by 2 over 3? Well, bring the whole term, the entire term, to the power of 2 over 3. And when you do this to the left side, you have to do it to the right side of the equation. So now look at this. We have log of x on one side, power 3 over 2 times 2 over 3. That will multiply to 1. And the other side is 8 to the power of 2 over 3. So if you use the calculator to find 8 to the power of 2 over 3, which you can obviously do very easily. So you want to bring the power 2 over 3 in the calculator. You got to divide, you got to keep the power 2 over 3 in brackets, actually, to avoid any, confusions with using bad math. So to avoid calculators confusions, sort of. So, or another way, which is kind of a clever way, you can write 2 to the power 3 for 8, and then you have 2 to the power of 3 still here. So log of x would equal 2 to the power 3 to the power of 2 over 3, which makes it 2 to the power of, so I'm just going to keep the colors the same here. So we have 2 over 3 times 3, which is basically a power of 2, right? So we have log of x equals 2 to the power of 2 or 4, right? So right here. And now we're ready to solve for x. Just convert the log statement into an exponential. So the base is going to be 10, and then to the power of 4. So the value of x in this case would be 10 to the power of 4, or 10,000, and that would be our solution. If you want to check and see if this solution is acceptable or not, so what you want to do is substitute it into the x inside the log. It's a positive number, so why not? It works. And the power in any exponential number can be anything, so the square root of it would be a legitimate answer, legitimate number. And there you go. This would be the final answer. Okay, so we have the next question, one more question. So the next question is sort of a thinking question. I will explain this in a separate video. And I thank you all for watching, and I hope that you found the explanations useful. Bye for now.